Welcome to this explainer, graduate engineers. Today, we're totally geeking out on the architectural fundamentals of GNSS, Global Navigation Satellite Systems. We're going to break down the exact algorithmic processing you absolutely need to build high-accuracy positioning software. Whether you're working on the navigation stack for self-driving cars or building out super-precise surveying tools, taking raw signals from space and turning them into centimeter-level coordinates is absolutely crucial. So, let's bridge that gap between theoretical physics and your actual practical code.
Okay, here's our roadmap. Number 1. GNSS architecture and system evolution. 2. Signal measurements and raw data. 3. Standard point positioning algorithms. 4. Parameter estimation using Kalman filters. And finally, 5. Precise point positioning. Let's get right into it.
Section 1. GNSS architecture and system evolution.
We really have to start by looking at the macro view, right? The physical hardware floating up in orbit. Looking at historical development milestones straight from European Space Agency technical documentation, the sheer evolution here is honestly mind-blowing. Think about it. Back in 1978, those early GPS Block 1 satellites were launched with just a 4.5-year lifespan. By 1995, GPS finally hit full operational capability. But then, jump to 2011 and 2012. That's when the first operational Galileo satellites launched. These absolute beasts weigh in at 700 kilograms and carry these insanely precise rubidium and passive hydrogen maser atomic clocks. That massive upgrade in hardware is exactly what dictates the quality of the data your software is crunching today.
And all this history really highlights the three main pillars of GNSS architecture. You've got the space segment, which is those satellites broadcasting away via atomic clocks. Then there's the control segment, basically the ground stations making sure the satellites stay perfectly on track. And finally, the user segment. Now, as software engineers, this right here is your domain. This is where your code lives, grabbing that raw data from the receiver and doing all the mathematical heavy lifting.
Moving on to Section 2. Signal measurements and raw data. Let's transition from the hardware in orbit to the physics of the signals they're actually spitting out, because this is the true lifeblood of your positioning algorithms. The foundation of any high-accuracy software totally relies on two basic observables. First up is the code pseudorange. This uses pseudo-random noise sequences to calculate a rough travel time from space. Second, we have the carrier phase, which looks at the actual radio frequency sinusoidal signals. So why do we need both? Well, pseudoranges give you a really solid ballpark estimate. But locking onto that carrier phase is the absolute secret sauce for pushing your algorithms from meter-level accuracy down to strict centimeter-level precision. But here's the catch, and you know this. Measurements in the real world are never perfect. The gap between your measured ranges and your predicted ranges leaves us with what we call pre-fit residuals. These tiny leftovers contain your receiver positioning errors, clock offsets, and just general everyday noise. The entire mathematical goal of your code is to successfully decorrelate those specific errors from the residuals so you can uncover the true geographic coordinates. It's basically a giant puzzle.
Section 3. Standard point positioning algorithms.
With our raw data and residuals defined, it's time to dive into the algorithms. If you're sitting down to code a robust GNSS standard point positioning, or SPP solution, whether it's for a graduate lab exercise or a commercial software tool, this is your logical workflow. Step 1, you collect pseudo-range measurements from at least 4 satellites. Step 2, you compute those pre-fit residuals we just talked about. Step 3, since satellite-to-receiver ranges are highly nonlinear, you have to linearize the geometric range in the neighborhood of an approximate position. And finally, Step 4, you apply a mathematical adjustment to estimate the exact coordinates.
And what exactly is that adjustment technique? Well, it's almost always the least squares condition. By applying least squares, your software actively minimizes the squared discrepancy between the noisy measurements you gathered and your fitted mathematical model. It's all about finding that absolute minimum. It iteratively guides your code, zeroing in step by step to accurately estimate exactly where the receiver is.
Section 4. Parameter estimation using Kalman filters.
Now, least squares is great, but it definitely has its limits. Because our applied models are imperfect and measurements are inherently noisy, we have to level up to advanced parameter estimation. Grounding our math in its historical engineering context, we look back to R.E. Kalman's brilliant 1960 paper. Kalman's optimal stochastic observer, the legendary Kalman filter, is an absolute cornerstone in aeronautics and astronautics. It's literally the premier method for merging dynamic system models with noisy satellite data, providing vastly superior state estimates over time.
What's truly powerful here is how you actually apply this in your code. You can augment unknown plant parameters directly into your state variables. By structuring your state vector matrix this way, we're treating an unknown parameter like the actual mass of the vehicle as a dynamic state to be estimated right alongside its physical position. It's a really elegant way to handle unknowns.
Next, let's consider the dynamic matrix to see how this builds directly into the system dynamics. This matrix calculates exactly how those unmeasured states evolve over time. By combining your noise statistics with the physical dynamics of the vehicle, your filter continuously predicts the next state and then, bam, it instantly corrects itself the millisecond new GNSS data arrives.
When you run your testing protocols to validate your precision, this is exactly the kind of result you want to see. These visual proofs totally demonstrate the power of the extended Kalman filter. On one hand, you have the filter successfully converging on the vehicle's true mass. Because the software learns that mass on the fly, it directly results in a drastically reduced position error. Estimating physical parameters in real time makes your navigational accuracy absolutely skyrocket.
Section 5. Precise Point Positioning, or PPP.
For applications that demand the absolute highest performance, we leave SPP behind and upgrade to PPP to achieve true centimeter-level precision. But to hit that mark in your software, standard broadcast data just isn't going to cut it. Your algorithms have to meticulously ingest a whole bunch of advanced modeling terms. We're talking precise satellite orbits, highly accurate clock offsets, real-time ionospheric corrections to handle atmospheric delays, and you absolutely must estimate carrier phase ambiguities. It's a massive data upgrade.
Historically, classical PPP algorithms were painfully slow. It could take an hour or more just to converge to a 10-centimeter error level. But modern fast PPP, it completely changes the game. By successfully integrating those precise real-time ionospheric corrections into the filter, fast PPP drops the convergence time down to just a few minutes. Literally, from an hour to minutes. This is a massive leap forward for real-time kinematic software.
So as you head back to the lab to code tomorrow's navigation tools, I want to leave you with this thought. GNSS is incredibly powerful, but it completely relies on having clear visibility of the sky. So how will your software fuse these optimal GNSS estimation techniques with localized inertial navigation systems? Creating perfectly stable error fallbacks for autonomous vehicles navigating deep urban canyons or tunnels, places where the sky is totally invisible, is the next great frontier in engineering. How are you going to solve it? Thanks for joining this explainer.